Hello class, welcome to this video on the lesson practice for checking normality. So we're going to go over the last two problems in the practice. So let's go ahead and get started. So there are three tests that we discussed in class. So we're going to go through each of those tests. So they're going to take some time, but let's get through them. So we have some box office revenue data in 2009 for some top grossing films. So let's see here. We have... It seems to me that we have 1, 2, 3, 4. Looks like we have 24 data points here. So we want to determine if they follow a normal distribution. So let's go ahead and look at the test 1, which is a lot of stuff involved, right? This the histogram, outliers, and the Pearson coefficient. Okay, so let's go ahead and do the histogram first. So let's choose, for our example, let's choose 7 classes. Remember that you can choose a minimum number of 5. So I'm going to choose 7, just random. You can choose 5, 6, 7, 8, whatever. And then based on the number of classes, your histogram might change slightly. Sometimes it might be hard to tell what shape it is. Sometimes it's not. This is why we have the outliers and the Pearson coefficient as backup. To help us with our conclusions, okay? So don't worry too much about that. So we need to calculate our class width, which is our range divided by the number of classes that we chose, which we chose 7. So in order to do the range and stuff, it's probably easier to just sort the data. So that's one of the first things we're going to do. So let's go ahead and sort the data here. I'll go ahead and sort it here. And then when I sort it, we'll come back. All right, so we went ahead and sorted all the data points. So we got 28 as the smallest and 402 as the largest. Okay, so we got the data sorted. So now we are going to take the range, which is the maximum minus the minimum. So 402 minus 28 divided by the number of classes is 7. So if we do that, we get 53.43, which remember that when we're doing the class width, we're always going to bump it up. So we're going to bump it up to 24. So we always round up, irregardless of like the decimal. Now, if we got a whole number, right, like 53, then we'll most likely gonna bump it up as well to 54. But definitely you're gonna round up in most cases here. So we got 54 as our class width. And then we're going to set up our table, our frequency table. So we have our interval or our class. Let's just call it our class. And then we have our frequency. So we're going to start with the smallest data point, which was 28, right? And we're going to add 54 to that. So 28 plus 54 is 82. Now we got to do 24 plus 82. Hold on, let me make sure this is right. Or 54, I said 24, sorry. 82 plus 54 is 136. And then you get 190, and we're going to stop until we get to 7 classes. That's how many classes we had. All right, we're almost there. So we got 352 to less than 406. So that's 2, 4, 6, 7 classes, okay? So now we're going to take our ordered list and see how many numbers belong in each category. So how many numbers belong between 28 and 81? I said 81 because that's less than 82. So from 28 to 81, including 81. So we got all of these numbers here all the way to here, right? So that's 16 numbers. So let's go ahead and put 16 here. And then from 82 to 136 is only 3 numbers. 82 to 136. Yep, that's 80 to 109 there in that case. Actually, wait a second. 82. So it's got to be 84, 109, 113, and 146. And then for the next one, it's going to be 3 numbers. And then there are no numbers between those two. There's only 1 number there, no numbers here, and 1 number for the last one, which is 402. All right, so those are the numbers that belong in each interval, okay? So now we're gonna make the histogram. Remember that the frequency goes on the y-axis, the class. In this case, the class represents, in this case, the box office revenue, right? Okay, so we got 7 classes. So the first one is 28, 82, and so on. Using our numbers from here. Okay, so we got those numbers, and then we need our frequency, so it's all the way to 16. All right, and we could have gone by 5s if you want, 5, 0, 5, 10, 20, and that's fine too. I just decided to go by 1s, but you can go however way you want. So between 28 and 82, we have a large, a box of a great height, all the way to 16. 82 to 136, we got 3. And we got another 3. And we got 0. We got 1. And finally, we got, we got 0, and then we got another 1. All right, so looking at this distribution, you can see it's definitely skewed to the right here, because it's peaking at around here, and then the data kind of tapers off, right? So we know it looks skewed to the right just by observing it. It appears to be skewed right. Now we're going to calculate the piercing coefficient to see if this holds true, okay? And in order to calculate the piercing coefficient, we need to know the average and the median and a standard deviation for this data set, okay? So we're going to need to do that. So we need to find the average, the sample mean, the sample standard deviation, and then we'll need the median, and then we'll need to calculate the piercing coefficient. All right, so to do the average, just add up these numbers, right? You're going to add up these numbers and then divide by, we have 24 of them, right? So we're going to add up these data points and then divide by 24. So if you add up these data points and divide by 24, you're going to get 90. Now to do the standard deviation, we'll show you how to do this. If you don't have access to like a scientific calculator or something, you can use Desmos to be able to calculate this. Okay, so if you type in Desmos Scientific Calculator on the browser, you'll have a pop-up here. So you click on that link, and you'll be taking a Desmos Scientific Calculator. And so this is really useful because you can type in your responses, and the good thing is you can see your calculations live, right? So you can see the data, exactly what you're doing when you do the calculation, and it has statistical functions as well. So if you click on function here, you have stdev, that's for the standard deviation. You even have permutations and combinations and factorials, so you have all that stuff. You have the mean, and you have the standard deviation p, which is for population. We want the standard deviation for the sample, so we're going to choose this. So you hit that, and then you start typing in your data. So let's type in our data. This is the data that was in order, right? Let's see. Let's type it in order and see what we get. Okay, so if you look at the standard deviation, it appears to be 89.6, okay? So that is our standard deviation. Let's go back here. And hold on, let's go take a look over here. All right, so we got standard deviation is 89.6 approximately. All right, really useful calculator. So now And you know, there's other calculators on the browser, but I would say that's probably one of the more useful ones. Now let's go ahead and do the median. So to do the median, that's the middle number, right? So we're gonna find the middle number. Since we have 24 numbers, that means there will be two middle numbers, right? So we just gotta be careful. Okay, so we got 1, 2, 1, 2. Work our way towards the middle. Let me cancel out as I go. 1, 2, 1, 2, 1, 2, 1, 2. Okay, there's one middle number in my example, so I think I missed a number. Okay, I missed a 32. So let me go back real quick, because I missed a 32 in my ordered list. So let me go back right here. So I forgot that. Okay, so it's going to cross my 1, 2. All right, so we got between 52 and 66. Okay, so that means we got two middle numbers here. So we're going to add them up, divide by 2. 52 plus 66 divided by 2. All right. So let me get rid of all of this, all these marks here. Okay, so we got between these guys. So you get 59 if you add them up and divide by 2. All right, so now next we're going to need to calculate our Pearson coefficient. So to calculate this, you do 3 times sample mean minus the median divided by the standard deviation, the sample standard deviation. So we got 3 times, we got 90 minus 59. And we can clearly see that since the average is greater than the median, that means that indicates that this is going to be skewed to the right. Okay, so if the average is to the right of the median, it's going to be skewed to the right. So we got divided by 89.6. Now, is it significantly skewed to the right? That's what we want to find out. Is it significant or not? So let's calculate that and see what we get. Actually, I'll do this over here since we can type it in on the computer. So if I need to put a times here. Let's see if that works. Okay, there you go. So we got 1.04. So that is greater than or equal to 1, which means that it's significantly skewed to the right. Okay, so that means it's significantly skewed right. Okay, so that basically confirms that it is skewed to the right, but, and so we concluded that here, right? But let's go ahead and check the outliers just to be safe, because that's part of the test as well. So let's go ahead and do the outliers. Now remember, to do outliers, we need to know the first and the third quartiles and the interquartile range to be able to identify outliers. Okay, so to do the first quartile, so we know that this is the median right here, which is about 59. That was the median, which is the second quartile. So now what we're going to do is we're going to go to the left here and figure out the middle. 1, 2, 2, 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we got 12 numbers. So we have two middle numbers, but so that means the first quartile is in between them, but since they're both the same number, 32 plus 32, the first quartile is 32. But let me just show my work here. 32 plus 32 divided by 2 is still going to be 32. All right, and then let's take the third quartile, do it to the right side for the third quartile. So 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And so it's between these guys, right? So the third quartile is 109 plus 113. Divide that by 2, see what we get. So 222 divided by 2 is 111. All right, and that makes sense. 111 is halfway between 109 and 113, so that makes sense. All right, so now the interquartile range is the third quartile minus the first quartile. Okay, so you're going to subtract those together, and that's going to be 79. All right, so now we got that. Now we can determine the outliers, okay? So remember that the bounds for the outliers, there are two of them, right? There's a lower bound and an upper bound. And so remember that if x, which is the data value, is between these two bounds, then it's not an outlier. If it's not between these two bounds, then it is considered to be an outlier, okay? So to get the lower bound, we take the first quartile and we minus it by 1.5 times the IQR, okay? So the lower bound is first quartile minus 1.5 IQR. The upper bound is third quartile plus 1.5 IQR. All right, so 32 is my lower quartile, so 32 minus 1.5 times 79. And then my upper bound is 111 plus 1.5 times 79. All right, so let's go ahead and figure out what those are. 32 minus 1.5 times 79. So that's negative 86.5. That's pretty low. All right, let's do 111 plus 1.5 times 79. So that's 229.5. All right, so that means if there's any number that is outside of that range, then it is considered to be an outlier. So in this case, we do have some outliers, right? Has to be greater than 229 to be an outlier or less than this negative number. There are no numbers less than negative 86.5, so we're good there. So let's look at the 229. So for the 229, this is greater and this is greater. So we have two outliers, 277 and 402. So two outliers. And then 402. So we have two outliers that are greater than, that are on the right side. So this indicates that it's definitely skewed to the right. So therefore we can conclude that it's not normal, right? This is not a normal distribution by the first test. All right, that's test 1. Let's go ahead and look at test 2. All right, so test 2, we're going to look at the normal, the quantile plots, okay? So normal quantile plot. All right, so in order to do this, we're going to need to basically sort our data, right? We're going to have our data, we're going to have the area, and we're going to have the z-score, okay? So basically, what the short version is you take the number of data points. So we have 24 data points, right? And then you multiply it by 2 to get 48. So 24 times 2 is 48. Okay, so that's going to be your denominator. And so each of these areas are going to be 1 out of 48, 3 out of 48, 5 out of 48, and so on. They're going to be odd numbers, 1, 3, 5, 7, 9. Okay, so that's all you need to know. It's to get the area under the curve, right? For each of these values, for the quantiles, you multiply the number of data points by 2, and then that's your denominator, and then you have basically, you're going to start with odd numbers starting at 1, okay? And this is sorted. Remember, this has to be sorted in order so that your smallest number has an area of 1 over 48 under the curve. All right, so let's go ahead and write down our data points again. So we got 28, 30, 32, and so on. So let's go ahead and do all these data points. All right, so all these data points. Let's do the area. So this is 9 out of 48, 11 out of 48, 13 out of 48, 15, 17, and so on. Then we're going to convert each of these to decimals. All right, so I went ahead and wrote down all the values all the way to 47 out of 48 and converted them to decimals. So 1 divided by 48 is 0.0208 and so on. Okay, so we got all of the decimals for the areas. So now what we do is we convert these areas to z-scores. So we're going to get as close as we can to 0.0208 on the area for the standard normal distribution table. Okay, so we need to get as close to 0.0208 as possible. So 0.0208. 0.0208 right here. Looks pretty close, right? 0.0268. 0.0202, right? That's 0.0202. This is 0.0207. So that's the closest to 0.0208. And so the z-score for that is negative 2.04. So it looks like negative 2.04. All right, so we'll go over here and say this is negative 2.04. And that's what you do. So you do this for each of these areas. Now, the good thing is we only have to do half the values because half of the values are going to be negative, half the values are going to be positive, okay? So that's the good news, is we only have to do it for some of these. All right, so we went ahead and found the rest of the z-values using the areas here and looking them up on the table, okay? All right, so we got all the z-values, negative 2.04, and then notice that it becomes symmetric, right? So these values tend to repeat. So you only really have to do half of the values, and then after that, they start repeating. Okay, so now the purpose of this is to make a graph, the normal quantile plot. So this is going to go on the y-axis, and then the data is going to go on the x-axis, okay? So you're going to have essentially you're going to have a z, your z-score here, right? And your middle is going to be 0, right? And you're going to have your data here. So this is going to be your x values. And so what we're going to do is we're going to scale this. So it's going from 28 to 400, right? So from 28 to 400, we got a lot of numbers that are, so let's see here. Let's go by 50s, and then that should be okay. Okay, so a lot of the numbers are going to be smaller than 50, so we just got to keep that in mind. And let's start at 25. Yeah, let's start at 20. Okay. So let's actually just do 50, and then we'll space them out pretty nicely. Okay, and then our highest z is 2, and our lowest z is negative 2.04. So let's go by 0.5s for the z. Okay, so now we got our x and our z, and all we're going to do is we're going to plot the data. So we got 28 is negative 2.04, 29 is negative 1.53. So negative 1.04, wait, negative, let me take a look. Yeah, so 28 was negative 2.04. Around on here. 29 is negative 1.53. 30 is negative 1.26, which is right around here. 32 is negative 1.05. and so on. So we're going to keep plotting these points until we get our graph. All right, so taking a look at the data. So if you plotting all the data points, you can see that it's not very good as far as resembling a line. So that's just an example of a line of best fit. But yeah, you can see it's clearly not linear from the graph. So it's not linear, which means a normal quantile plot indicates that it's not normal. So we're going to say that it's not normal. All right. All right, so that's our test 2. So let's do our test 3. So our test 3 is our normal probability paper. It's using normal probability paper. So it's essentially a normal plot like the other one is, but actually using the normal probability paper as opposed to doing z-scores and stuff. All right, so what we need to do is basically we need to reiterate the intervals that we did earlier, and then instead of doing frequencies, we're going to do cumulative frequency and then cumulative frequency percent, okay? Okay, so let's take a look at, so we're gonna just kind of copy down the values that we got earlier. So we got, these are the values from the histogram that we did last time. Okay, so last time this was had a frequency of 16. Okay, so that means that the cumulative frequency is also 16. Last time this had a frequency of 3, right? So this was 16, 3. These were the numbers 16, 3, 3, 0, 1, 0, 1. This is from our histogram from test 1. So cumulative frequency, you're just adding these as you go. So 16 plus 3 is going to be 19. 19 plus 3 is going to be 22. And 22 plus 0 is 22. 22 plus 1 is 23. 23 plus 0 is 23. 23 plus 1 is 24. Okay? And then we're going to do cumulative frequency percent. So we're just convert this into a percent. The highest, the total is 24, right? So it's 16 out of 24. 19 out of 24. And then that's going to be 24 out of 24, which is 1. So this is 100%. Let's convert all of these into percent. So 16 out of 24. So that's 0.67%, or 67%, sorry. So that's 79%. So that's 92%. And that's 96%. Okay, so those are our values that we use. So this is going to go on the y-axis. This is going to go on the x-axis, the interval. Okay, so this is our normal quantile or normal probability paper, right? So so in this case, on the y-axis, we have our cumulative frequency percent, right? On the x-axis, we have our intervals or our classes, same thing. So our classes, remember, were 28 to 82, 82 to 136, 136 to 190, 190 to 244, 244 to 298. The next one is 352, and then 406. Okay, so those are my classes. And remember now, the first number is always going to be 0%. Then the number after that is going to be the percent that we got when we calculated it. So when we calculated it, we got 16%, right? So 82 is going to be 16%, which is around here. And then 136 is going to be 2%, and so on, right? All right, so that's 16. This one's 19. So that's pretty close to 20. And then 190 is going to be another 22%, Well, actually, no, we got 19% here. So this one's going to be 22%, and then the next one's going to be 22% again. 22 is around here. So another 22% for this guy. The next one was 23%, so it's only slightly above that. And then the next one is still going to be 23%. Oh, I'm sorry. I'm looking at the wrong numbers. Okay, so this one is 0. This one is 67%. I'm sorry. No wonder the numbers were a little weird. So I'm trying to go back. So let me go back to my table, to the table. So yeah, we have 67, then 79. Okay, so let's use those numbers. So 67% for 0 for the first one. Second one is 67-ish. Next one is 79%, just close to 80. And then 92. And then another 92. And then 96. And then another 96. And then 100 for the last one. Okay, so we have, if we look at this data, it does not appear to be all that linear. Okay, so we're gonna say that based on this, it's not linear. Okay, so now the next thing we're gonna do is we're gonna calculate the R value to see what the R value is for this, just to make sure that everything's good. Okay, so we're gonna calculate our R value, although it's not really necessary, but this is just to be able to make sure that we calculate our R value just to be on the safe side. Okay, so there are tons of correlation coefficient calculators out there. Just type in correlation coefficient calculator, and then you can go. They'll go ahead and ask you for your X value, your Y value, and then you can just calculate the correlation coefficient. Okay. So we're going to go ahead and just type in our numbers and see what we get for our correlation coefficient here. So remember that in this example, the X values are straight from the data, right? So in this case, I have 3 and then 17 and so on. Okay, so I went ahead and I used another correlation coefficient calculator. I put in the X values here, so I separated by commas, and then I put the Y values. The Y values are the Z scores that we got earlier. Remember, we got a Z score of negative 2.04 and so on. So these are the Z scores that we got from the second test. So we calculate it and see what we get. So if we go here, all right, so I will show you another way that you can use to basically calculate these things, like the correlation coefficient and all that. There was a lab that you could that we would have done for this, but we just didn't have enough time in the course. So if you go to Excel and you type in your numbers, these are my numbers for the X for the data, and then these are my Z scores. Okay. So what you can do is once you have those numbers typed in, then you can use to calculate the correlation coefficient, you type in equals Correl, C-O-R-R-E-L, and this returns a correlation coefficient. Then type in parentheses, and then you highlight your X values, comma, and then you highlight your Z values, and then you enter, and then it gives you your correlation coefficient. So the correlation coefficient is about 0.8. And so if we go back to our data, this is about 0.8. Remember that we want this to be close to 1. We don't want this to be that far from 1, okay? Even though 0.8 is kind of high, we want it to be closer to 1 than anything else. And based off of this, it's not good enough, okay? It has to be like in the 0.95s, it has to be pretty good for the correlation coefficient. All right, so that's going to do it for that problem. Let's take a look at the next problem. All right, so we have the next problem, which is a number of runs made by Bill Mazeroski's career. Check for normality here. So the first one, we said that it was not normal. Let's take a look at this one to see if it's normal, and go from there. So for this problem, I'm gonna just kind of go through and do the information and then go over the results with you, just to save some time. All right, so this is the first test. So test one, went ahead and went through the calculation. So we sorted the data from 3 to 71 all the way here. And I chose to do 5 classes. You could choose whatever classes you want. If I did, as long as this is a minimum of 5. So you got 71 minus 3 divided by 5. 5 classes is 13.6, which is about 14. And so I went and I used the smallest number 3 and I added 14 to it, the class width, right? And I got a total of 5 classes, and then I figured out, okay, well, there's 2 numbers between 3 to 17. Well, that's these 2 numbers here. And I got all the frequencies, and then I made the frequency histogram here. And you can kind of see that it looks kind of skewed to the left, right? But it's hard to tell if it's strongly skewed to the left or not. And so what we're going to do is we calculate the average, standard deviation, and the median, and we calculated the Pearson coefficient, and we got negative 1.43, which means it's strongly skewed to the left. Remember that if it's beyond -1 or beyond 1, it's strongly skewed. So we got the outliers, the first quartile, the third quartile. So we knew the median was 52, so I went ahead and figured out the first quartile and the third. The third was between these 2 numbers. The first was between these 2 numbers. Added them up, divided by 2. And so then I calculated the interquartile range, subtracted those to get that. And then we plugged it in to get outliers. So we took the first quartile minus 1.5 IQR. We took the third quartile plus 1.5 IQR. And we ended up getting these 2 numbers. And so based off of these numbers, there are no outliers that are present. So there are no outliers, okay? So this doesn't give us much information, unfortunately. We kind of suspected that there might be an outlier on the left side, but there isn't, and so that's okay. That just means there are no outliers. There's no other information that it can tell us. So between this and the fact that the Pearson coefficient and the histogram tells us enough information, we can say that it's not normal. All right, we're going to take a look at the second test. All right, so this is the second test. So I went ahead and sorted the data. So we got the data here from 3 to 71, and then we did the area. Now remember, since we got 17 data points here, that means we multiply that by 2, and that's how I got the 34 here. And remember, we have 1, 3, 5, 7, 9, 11, and so on. So this 0.2059 I got by doing 7 out of 34, then 9 out of 34, 11 out of 34, and so on. So that's how I got these areas. So 1 out of 34, 3 out of 34, and so on. And then I used the z-table to get the z-score from this area. So if we go back to, let's say, see if I can find it here. So if we go back to here, yeah, the z-table here. So if we looked up 0.029, for the area, .029. These are really close to 0.029, right? 0.029, because it was 0.0294. So that's probably one of the closest ones. This is the closest to that, 0.03. And so that's going to be negative 1.8, negative 1.88. So that's how we got that value. Okay, so let's go back here. So negative 1.88, negative 1.89-ish, right? So that's how we got that around there. And then, so that's how we get the rest of the z-values. And then we graph them, and so we get something that looks like this. Now, when you look at this pattern, you're going to say, oh, it kind of looks linear. But no, what you want to look for is it's got to be exactly linear or really close to it. So even if there's a little bit of variation, that probably means it's not normal, okay? Because what you want to notice is that if you look at this pattern, you have sort of like this zigzaggy pattern. You don't want any waves in it. So for example, this one has a generic wave that looks like this, and then it kind of goes like this, right? So if it has sort of like a wave where, you know, you have this upward part and this downward part, that makes it kind of like a snake-like shape. You don't want any snake-like shapes for this, okay? Snake-like shapes for this, or sigmoidal shapes, indicate that it's not normal, okay? So this is not normal. No linear patterns, okay? There is actually there's some curvy patterns to it. All right, so this is not normal. So we're going to take a look at the last test, test 3, and we'll do that, and then we'll share the results. Okay, so for test 3, remember, all we got to do is basically reiterate the frequency table that we had earlier for the histograms, and then calculate the cumulative frequency. So remember, the cumulative frequency is when you build up from the original and work your way down. So the original is 2, and then it's 2 plus 3 is 5, 5 plus 2 is 7, 7 plus 5 is 12, 12 plus 5 is 17. So at the end, we should end up with our total. And then the percentage is 2 out of 17, 5 out of 17, 7 out of 17, which is 41%. 12 out of 17 is 71%. And then 17 out of 17, of course, is 100%. So that's how we got those. And then we're going to need to graph them in our normal probability plot. Okay, so we're going to graph those guys. We can go ahead and show you that graph. So let's go to the normal probability paper. Again, we have our cumulative frequency percent, also known as cumulative relative frequency, same thing. And then we have our data, which I'm just going to say class. So we got 3, 17, we got 31 for our numbers, 45, 59, and 73. So those are our numbers for our intervals. All right, so for the first one, remember we start at 0 for the first one, and then the second one we start with our cumulative percent, which if you go back earlier, we got 12% there. So we're going to go to 12%. And then 41, so we got a big jump to 41% right here. And then the next one is 71%. And then the last one, it goes to 100%. Okay, so we take a look at our data here, and starting at 0, take a look at this pattern here. Can you see that curvy pattern in the data? So if you see a curvy pattern in that data, that sigmoidal shape, that indicates that it's not linear. And so therefore we can stop here and say it's not going to be normal. So when you actually have a normal distribution, the data point is going to be really close to they're going to be really close to the line when you do this, because this is a very special graph. Notice that this graph starts over here at 50, and look, and this is a spacing of 10, yet it's so closely spaced together. And then notice that the spacing goes farther and farther apart, right, as you go out, as you go here and here. And so it's a specially designed graph to basically be sensitive to changes in the data. And so if the data is not following the pattern that it's supposed to, you can easily tell that it's not normal, okay? So this is not a normal distribution. All right, that's going to do it for the video, guys. I hope you found this useful and informative. And as usual, I'll see you in the next one.